So sorry for not being there. I arrived 2 days ago to Gainesville, in Florida, to start my postdoc here with Alan Ginsberg, and that's not here. So what I'm going to present today is part of what I did during my PhD with Javier Goicoechea in Madrid and the ORION-V team. And this project mostly focused on the role of HCN as a tracer of the dense gas reservoir for star formation. Why HCN? Well, the thing is that in star formation studies, they have this Kennicutt-Smith law, which is an empirical relation between the star formation rate and the dense gas mass, sorry. So they use different tracers to derive the star formation rate and the gas mass. For example, Kennicutt in 1998 found that the far infrared luminosity correlates or is a tracer of the star formation rate. On the other hand, for the gas mass, in extragalactic studies, they mostly use the low rotational lines of the CO, the luminosity, to trace the molecular gas mass. However, the relationship between the far infrared luminosity or other star formation rate tracers and the CO luminosity is not linear. And astronomers like things that are linear. Their relationship is linear. So Gao and Solomon in 2004 published a survey of nearby galaxies and found what you can see here in this figure, and is that the HCN luminosity is linear in the log-log scale with the infrared luminosity. So they thought that the HCN luminosity is a better tracer of the star-forming gas. Actually, traditionally, the HCN is considered a tracer of the dense gas. This is mostly based on the critical density that is a few times 10 to the 5 centimeters to the -3. So extragalactic studies use the HCN emission as a tracer of the star formation or the star-forming gas in galaxies. Actually, what they mostly consider, or what they think they are tracing, is gas with densities above 10 to the 4 centimeters to the -3, and actually from the work of Lara et al. 2010 and 2012, they would be gas with a visual extinction above 8 magnitudes. So going back to the ORION-V, Ian did a very nice introduction on this with the filaments and everything. So I hope you morely know where filaments are. So here in blue, you can see the distribution of the HCN emission. Well, in red is the visual extinction, and in red is the emission of the dust at 70 microns. So the important part is that the HCN not only emits from the filaments, so from here or from here, that this would be like ORION-V9, for example, not only the filament, but is also extended. And actually is kind of maybe related, we'll see later, with the when there's ultraviolet radiation. So here, when you can see the red area. So some tools that we use in this project are, for example, the dust thermal emission. So what I did was to feed the spectral energy distribution to derive the far infrared intensity and then the G0. I use the dust temperature and column densities from Lombard et al. 2012. What we see here is that that the G0 is higher in the H2 regions, like in NGC 2024 that Ivana talked about, then NGC 2023, and then the edge of the ORION-V cloud. Other goals or models that we used was the non-LTE radiative transfer code to model the hyperfinite structure HCN emission. So HCN, instead of having a single line for each rotational line, is split into a hyperfinite structure. So it has 3 lines in this case. So the codes included the line overlap effects and collisional excitation both with H2 and with electrons. This is the HCN emission in Orion B at 120 arc seconds. Here, the contours are the visual extinction ranges, so 4, 6, 8, and 15 magnitudes. And what I would like to remark here is that there's a lot of HCN emission. So outside the 4 magnitudes contour. Let's see what this means. So this is what we're going to understand in this project. The HCO plus also shows a very extended emission as HCN. However, HCN shows a more compact distribution, more focused, more only concentrated in the filaments. Last but not least, I got the atomic carbon line at 492 gigahertz. This was mapped with a telescope in Japan in the late 1990s. What is also important here to see is that the emission is also very extended, and if we detect atomic carbon, it's because there's ultraviolet radiation. So it's extended in the cloud as well. If we compare the line intensity distribution as a function of the visual extinction, we see we compare the CO with the HCN, and we have here the ranges for the 4 magnitudes. So the diffuse gas is below this line, and about we have like a translucent gas, dense gas, and the very dense gas above 15 magnitudes. If we get the percentage of the luminosity of each line per visual extinction range, to summarize this figure, what we see is that around the 70% of the HCN luminosity is associated with gas below 8 magnitudes of visual extinction. So mostly all the HCN emission arises from gas that is not associated with the star formation. So translucent or diffuse gas, low density gas at the end. One thing that we also did in this project is that, well, in extragalactic studies, if they assume that HCN is tracer of the high density gas, and CO is a tracer of the total molecular mass, the ratio between them would be the dense gas fraction, okay? So these would be justified in this histogram with these branch of the histogram. So here we find the AV versus the ratio of HCN versus CO in densities. So this branch is the dense gas. However, in Orion V, we have a second branch that have an increasing ratio to lower AVs. Actually, if we represent this ratio, like the spatial distribution of this ratio, we actually see that there's high values in the filaments and outside the filaments, mostly in the edge of the cloud. If we also compare this part of the histogram with the atomic carbon versus CO emission ratio, well, this ratio is, according to low density PDR models, is inversely proportional to the molecular gas density. So what we see here is that the atomic carbon to CO increases as HCN to CO ratio increases. So as the density decreases here in the left-hand side histogram, the density decreases. So in the context of a very large-scale emission from giant molecular clouds, or for example, in forest galactic studies,
we have 2 minutes left.
Okay, this overlook component could result in overestimated dense gas fractions. So we say that we have a deeper finite structure of HCN, and what we found for the 1 to 0 is that mostly all the relations between the lines are anomalous. We can discuss this later. We also observe with the 30 meters telescope more rotational lines of the HCN, and actually what we see is that not only the hyperfinite structure relationship between the lines are anomalous for the 1 to 0, but also for the 2 to 1 and 3 to 2. For the Futur 3, they are not resolved. Sorry for being like very fast with here. We compare the histogram of the HCN emission in Orion V map with the models that I commented at the beginning. These models have different temperatures and different ionization fractions. So the electrodes here. What we see here is that the faint emission that is related with the extended component can be reproduced in the models if the emission is low. So if the density is low, so around 10 to the 4 for the median value, or lower if the ionization fraction is above 10 to the -5. So what we have is that less than the 5% of the total HCN luminosity is associated with the very bright emission parts. So the bright and compact regions where the star formation is happening, and so where the density is high, and around the 70% of the total HCN luminosity is associated with the faint and extended component in Orion B cloud. And I wanted to finish with the relationship between the line intensity and the far infrared intensity. This is similar to what it used in extragalactic studies. So the Kenny-Kada and Smith law. What we can see here very fast is that for the CO, HCN, and HCO plus, when we feed the histogram for all the pixels, we get power loss with values similar to those used in extragalactic studies. If we go to the part where the far infrared intensity is high, so that associated with the high mass star forming regions in Orion V, the power law is very high, so is super linear, while the low far infrared intensity, the faintest emission of these lines is associated with the extended component, and the relationship is sublinear. However, to finish here, the HCN histogram that is down here, if we can feed all the histogram with a single relationship that is super linear, and according with other part of the project that we've done, this is a good tracer of the dense gas and the star forming gas in Orion V. And I stop here. Sorry for not being on time.
Thank you very much, Miriam. For one quick question, yes?
Yeah. So can you go back to the relation of the extinction and the integrated intensity of HCN I saw that you have detected HCN at extinction of just at this figure, just a few percent of. It's just 0.43, and so is this a real detection? Because in this extinction rate, it's just from the H1 to H2 transition. I'm wondering if these data points are real detection.
So all of them are real detections at 120 R seconds, not at 30 R seconds. So the noise is lower at this spatial resolution, so the signal to noise ratio is better. That's why these are real detections, about 3 sigma. Does that answer your question?
Yeah, and another question maybe related to the excitation, because at this extinction range, the gas volume density are supposed to be low, and then the HCN emission would be subthermal excited, and then it's hard to be detected in emission line, I guess.
Yeah, this was not easy to detect. That's why I smooth the maps to 120 R seconds to recover all the extended emission.
So there is another question online by Haohi. Do you want to? Yes, please.
Sure. Yeah, I can ask. So yeah, also the plot you showed before on the HCN versus this one. I just wondering, like, it seems like so seems CO intensity is like plateau earlier than the HCN, but I was wondering if it's possible that it's because CO is optically thick, so in that high column density region, it's just plateau early. Yeah. Instead, like it's like a HCN tracing dense gas. Would you have some thought on that?
Yeah, for the CO. Yeah, I think actually the Petit et al. 2017 focus on that part of for the CO. Why it's not tracing the AV? Why it's saturated?
Yeah, I mean, like maybe it's just because CO is optically thick and HCN is optically thin. But...
Yeah, but here the important part is that we have most of the HCN points associated with AVs lower than 4 magnitudes. So it's low density gas.
Okay, low density gas. Okay, I see.
Yeah, so this is the important part in this figure.
Okay, I see. Okay, sure. Thanks.
There is another question online. No?
No, we have no more time.
Okay, sorry, Ashley. Please ask your question on the Slack, and we'll on the chat and
right in the chat. Yeah,
you can write me Ashley later if you want.
Thank you again, Miriam.
You're welcome. I'm observing.
Thank you.
Thanks.